We have MUIR with low power vision processing and signal processing for IoT and edge devices. From SynSense, thank you very much, Dylan, for joining us. So the stage is yours. Thank you very much.
Thanks a lot, Olga, and thanks everyone for joining us today. Today, I want to talk to you a little bit about our approach for low power vision processing and low power audio processing. I'm the director of the algorithms and applications team at SynSense. I'm also the director for business development at SynSense. My background is computational neuroscience and engineering. In the past life, I've done a little bit of modeling of biological neural networks, but now I'm using my engineering experience to build artifacts that do useful and interesting things for edge devices. So SynSense is a hardware company. We produce ASICs for low power machine learning inference and for signal processing. I'll tell you a little bit more about our hardware as I go through. So tinyML means many things to many people. I'm sure everyone has a very strong sense of what tinyML means, but if you ask any two people, I'm sure they're not going to necessarily agree. So I just want to be very clear about what I mean when I talk about tinyML and what we're interested in. Our focus is really on low power, and by low power, I mean, sub 10 milliwatts on average, and real-time low latency tasks. And there by real-time, I mean less than 200 milliseconds, which is about human reaction time. The sorts of use cases that I'm going to talk about today are about continuous monitoring, obviously for IoT devices, edge devices, power constrained devices, and we're interested in use cases where you're close to the sensor, as close to the sensor as possible. So at SynSense, we explore a large number of possible use cases: audio, vibration, biosignal monitoring for health, surveillance, drones, etc. But today I'm going to limit myself to audio and vision applications. So I'll begin with vision processing. And I want to emphasize the difference here between vision processing and image processing. I'm not talking about image processing in a sort of a data center workload sense. I'm talking about vision processing, where you have a continuous stream of images coming in. And vision processing raises various issues that are separate from image processing, and one of which is the fact that you have enormous frame-to-frame redundancy between any two frames in a vision stream. So you can see, as an example here, if you look very closely, you can see that I'm moving my hand, but you notice that between the two frames, there's basically no difference. And standard image processing pipelines and standard CNN-based image processing pipelines in particular are not able to make use of that redundancy. They take each frame independently and have to process the information for each frame again from scratch, even though very little has changed from frame to frame. And so how can we make vision processing more efficient? One obvious approach, of course, is to look at the frame-to-frame differences. So here you can see emphasized that really is very, very little extra information coming in from the next frame. But it's not clear exactly how to efficiently calculate and make use of and compute over these temporal difference images based on standard images, standard cameras, standard compute hardware. So looking at temporal differences is one way to improve the efficiency of vision encoding. This is the approach taken by some special sorts of cameras that some of you are probably aware of, called dynamic vision sensors. These are event-based vision cameras. They are non-frame-based images, so they have image sensors where each pixel independently detects changes in light intensity, increases or decreases. When each pixel detects an increase above a threshold or decrease below a threshold, it emits an event encoding the location of that pixel, and it does so asynchronously. And so the change in the vision stream is encoded in real time. It's non-frame based. It's really fully asynchronous, and so therefore it's a very efficient representation of the vision stream. So you can see here and the animation, comparing the standard intensity imager and the simultaneously recorded event stream. When there's no motion, then there's really an extremely low event rate. So it's a very efficient encoding. So the question is, how can one make computational use of this efficient representation? And our approach is based on a event-driven convolutional core IP that we've developed in-house that is designed to work directly with these event-based vision streams. So we have in our architecture, each convolutional layer is a single computational core. These cores in the architecture is very scalable. We can assign as much or as little resources in terms of memory resources to that convolutional layer as required. We can reconfigure the numbers of features, the kernel sizes and strides, and so on. And we can, each of these cores operate asynchronously and independently. So we can configure an architecture with as many or as few convolutional layers and convolutional cores as we like. And we support, therefore, any standard convolutional architecture. So because we're using a convolutional architecture, we can make use of fairly standard training pipelines and standard network architectures from the deep learning for vision field today. The computational unit that we use is illustrated here. So we use asynchronous binary neurons. So that it's essentially a form of binarised neural network operating asynchronously in time. The communication between neurons is in the form of single bit events with a value of 1. So what you see here is a number of input synapses, input synaptic events, and a neuron state. So because we operate in an event-driven fashion, when we receive an input event, it has a value simply of 1. And so the process of multiplying by the synaptic weight and accumulating into the neuron state becomes simply an accumulation because you're just multiplying by 1. The neuron is based on integer logic. The neuron then has a threshold based on this neuron state and produces an output event. And so this is sometimes known as a spiking neural network. In this case, yeah, what you see here is what you get. It's an asynchronous binary neural network. So the first use case that I'm going to show you is an attention detection sensor, basically. So this would be for a handheld mobile device, and the device should sense if the user is interacting with the device or not. And it does so by distinguishing between a glance, which means that the user is looking directly into the camera, versus a non-glance or background. So the user is looking away from the camera, or there's no human head in the frame. So the idea is that our sensor would provide a smart wake-up trigger or a smart attention signal asynchronously, continuously to a mobile device. The goal for the use case is that it should be low latency, so it should be human response time, less than 100 milliseconds, and it should be operating at low power continuously, so less than 10 milliwatts target power. This is an example here of the various data classes that we have. So in the first case, we have a camera, a statically mounted camera with a person facing the camera. We also have the use case with a handheld camera with motion present in the image, as well as a human face, as well as background data where no face is present in the image. The convolutional architecture that we use is fairly standard. It's a traditional sort of bottleneck convolutional architecture with 6 convolutional layers and 1 dense readout layer. And here we have a low resolution input layer, 128 by 128 event-based vision layer. This is matching our smart single chip vision processor that I'll tell you a little bit about later on. So for training and optimizing these architectures, because it's a convolutional architecture, we can make use of industry standard tools. We have an open source library called Synapse, which you can check out at synapse.ai. This is based on Python with a PyTorch backend. For this particular architecture and application that I'm showing you now, we do simple backpropagation training of a non-spiking convolutional network trained on event frames. We can perform optimization in training to make sure the energy consumption is low. We perform hardware-aware quantization in training. And then in our library, we can do weight transfer to the event-driven spiking architecture. So this can be tested in simulation and then pushed down and deployed onto our development kit, onto our hardware. So what you see here is a demo, pre-recorded live demo. Unfortunately, it's not live, of exactly this architecture in action. Our engineer Tian is holding a DVS camera in her hand. This is running in inference. The model is running in inference on our development kit hardware. We're using a PC here in the loop for visualizing the DVS events and visualizing the network output. And so you can see here that the network detects Tian's face and ignores the background motion. And the performance of this network is quite good. So the median detection latency is less than 50 milliseconds. In fact, it's even less than 30 milliseconds. It's a fairly compact network, around 1/4 megabyte. The static power and the global average power, static plus dynamic, for our development kit running this model is around 10 milliwatts, less than 10 milliwatts. These are slightly pessimistic numbers. And for comparison with a standard CNN, it's always a little bit difficult, but the same architecture would require 62.1 mega max per inference. And so running at 20 Hertz, we estimate this would be on a low power AI chip would be around 64 milliwatts. So I have another brief demo here of a multi-class recognition task here. So this is obviously vision-based gesture recognition. Here you see Sadiq, my colleague, showing a number of gestures. Again, this model is running in inference on our development kit hardware with the PC in the loop for visualization purposes. And the model is correctly identifying and recognizing these gestures in real time. And the performance here is we have reasonably usable accuracy. We have extremely low latency and again, system global average power of less than 10 milliwatts. So shifting a little bit, sorry, I should show a nice picture of our development kit hardware. The development kit is available at small scale at the moment, but it is available. If you're interested, then please check out our website or you can contact me directly. We can discuss making one of these available for you. So shifting slightly to audio processing applications, we have a slightly different hardware architecture, which is tailored for continuous real-time signal processing, for example, audio processing. We're interested in various other type of continuous signal processing use cases, such as industrial vibration monitoring. There's various different speech or audio style use cases that we could deploy. Today, I'm just going to show you very briefly a schematic of the sort of wake phrase command detection use case, which I'm sure you're all anyway very familiar with. So here we would have a real-time audio input consisting of a wake phrase and then a number of different commands, and our system recognizes the wake phrase, distinguishes the individual commands. You can see here on the lower plot the detection signal as the output of the network, so you can get some sense of the timing here. But the performance of the model is good. The latency is human response time. We have good sensitivity to the wake phrase and pretty good false alarm rates. And the power consumption, so the front end audio is an estimation around 50 microwatts. The neural core is a measurement on our hardware that we're bringing up at the moment, and that's also less than 50 microwatts. So we have these two main families of hardware corresponding roughly to the two classes of use case that I showed you today. On the left, we have vision processors and single chip SoC vision devices. So Dynapse CNN is our development prototype for our convolutional cores. We also have SPEC, which is our single chip device that incorporates a low resolution DVS sensor, which you can see the bottom left. I'm not sure if you can see my cursor or not, but the bottom left of the die is a low resolution DVS sensor, and then the remainder is the convolutional cores. And the idea is that this is really a single device vision solution, smart sensor solution. You can deploy a full vision application in sensor on this. Then we have a number of general purpose spiky neural network accelerators, and these are tailored for the continuous signal processing tasks. So we have a digital SNN, which we're bringing up at the moment. And this is really for sub 300 microwatt worst case tasks. We also have a line of mixed signal spiking neural networks that have more sophisticated neural dynamics. So that's all I wanted to share with you this afternoon. Today, I'm very happy to take questions if there's still a couple of minutes remaining. Otherwise, I'd be very happy to talk to you in my Hangout session later on.
Thank you very much, Dylan. Yes.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SenseML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and SynSense.